Okay, in the first question, we've got a measurement in kilometres that we're looking to convert into one of the units that will match the options given. This is where our handy conversion chart on the back of our booklet is going to come in useful. This table you won't be given in exams. Do make the effort to memorise it. What you'll find is that kilo sits higher than the others, which means we're going to be going down our table, multiplying by 1000 for each step. So 0.3 kilometers multiplied by 1000 would put it into meters, but that gives us an answer of 300, not 3000, so we can rule that out. Centimeters isn't on our table because it's the only one that doesn't fit the pattern of 1000 per step. That one you go down by 100, so if we multiply by 100, oh, that is where we find we do get an answer of 30,000. So D is our correct answer. 0.30 kilometres is equal to 30,000 centimetres. Similarly, in the next question, we've got some conversions. This time we're getting everything in seconds, but we're given values in hours or minutes. Our second conversion table, again, not given in the exam, so do put the effort into memorising, will help us here. Seconds is a smaller value than any of these, which means multiplying. Now, the factor we multiply by between hours and seconds is going to be 2 steps, each equal to 60. So take our 2.6, multiply by 60 once, multiply by 60 again, and we end up with an answer 9,360. In the case of minutes, 1 step, but 1 step is 60 for an answer of 9,600. Now, process of elimination would mean we know this must be our final answer. We can double check though. What you don't want to get caught out with is thinking 2 hours and 34 minutes is the same as 2.34 hours. That's not the case. So take your 34 minutes and multiply it by 60 to tell you that's 2040 seconds, and add that to your 2 hours multiplied by 60 and then multiplied by 60 again to give you 7,200 seconds to get a final answer of 9,240. On to experimental procedures, and any time we do an investigation we're changing something to see if it affects something else while keeping the rest the same. Effectively we're asking ourselves, hey, does this thing I'm measuring depend on a change of something else that I am choosing or allowing to control? Which means our dependent is the thing that we're measuring to see if it's affected. The independent is the thing we're choosing or allowing to change, and we don't want something else that could affect our results to ruin them, so we are in control of everything else. Scalar vectors next. Our fact to memorise is that scalars include only size, not direction, and that if a non-scalar is used to calculate a value, that value cannot then be a scalar. What I mean by that is acceleration. Well, that's change in velocity. Velocity is not a scalar, it's a vector, so acceleration couldn't be. The non-direction including version of velocity is our speed. Distance doesn't include direction, but displacement, which is the vector version of distance, does. Forces are represented by arrows, which is a good indication that they do not have just size, but also have direction. Momentum, that's calculated again by taking mass and multiplying it by velocity, a vector, so that can't be a scalar. Then we can ask ourselves, okay, does it make sense to use a direction in a sentence? Could I say I've got a mass of 85 kilograms downwards? No, that doesn't really make sense. Mass only has size. Last but by no means least, temperature is a tricky one, because though it can have negative values, and we talk about the temperature going down, temperature itself does not include any direction. You couldn't have temperature north, east, south, west, forwards or backwards. That's our final scalar of these. Calculation questions offer us an opportunity to use our heist approach, again detailed at the back of our booklets. So in this question, what I'm seeing is that I've got a measurement in seconds, that's going to be a time. I've got a measurement in meters, that's going to be distance, and I'm asked for the speed. So I can look up in my equation list, if I can't remember it, an equation that links all of those. I recall though that speed is equal to distance divided by time. In fact, there's already a hint to that within the question. Always read all the way to the end of the answer line for any question, where the unit will likely tell you what you've got to do. In this case, I see m/s, meaning take a distance measured in meters, divide it by a time in seconds. Plugging those numbers into my equation leaves me with 980 divided by 4, keyed into my calculator, never taking the risk of doing mental maths when you don't have to give a final answer of 245. Same again on the next question, applying my heist approach, highlighting what I've got, including in this case emphasising it says they're travelling at 7 meters per second when they applied their brakes. 4, written in words, seconds later for time, they were at rest. That is a cheeky hidden value of 0 meters per second, and I'm asked for acceleration. Looking at my equation list, what I find is that acceleration is related to speed, which can also go by the name of velocity if a direction is included, divided by time. Specifically, it's change in velocity that I want. So what I am going to do is I'm going to work out my change in velocity first, knowing that change is always the final take away the initial value, which in this case means where we ended up, which was at 0 meters per second, take away where we started at 7, meaning negative 7 meters per second is the change. Acceleration then is equal to my change in velocity divided by my time. Plugging those values in gives minus 7 divided by 4, a negative acceleration because we're slowing down 1.75 meters per second every second. Newton's first law of motion is coming into play on these questions. Each one we treat individually, and we're looking effectively to see what the forces are in each direction, vertically and horizontally. In the first one, there's forces equal vertically, up and down, meaning a overall resultant force is nothing. And Newton's first law told us that acceleration is caused by resultant forces. If there's no resultant force, there's no acceleration. Now, I don't know if that was moving and it's carrying on moving at constant speed, or if it was stopped and it is still being stopped. Either way, saying no acceleration is accurate. Next one's a bit different. We've got 20 up and 10 down. Imagining them like a tug of war. 20 on one side and 10 on the other would be the same as having just 10. Specifically on the upward side, forces include direction. Your measurement of resultant should include direction, and we can carry that direction forwards into our description of motion. Because again, Newton's first law said resultant forces cause acceleration. So this is going to be accelerating, and specifically in the upwards direction. Now that could mean that it is falling but slowing down as it falls, or it could mean that it is increasing its speed in the upward direction. We can't tell which from this diagram, but we can tell that it is accelerating. Two different sets of forces here. You've got to consider the vertical and the horizontal independent. Vertical forces are balanced, no resultant force. Horizontal forces, there's an extra 5 newtons in the rightward direction. I'm avoiding using forwards or backwards. Always just use directions as you see them on the page. Up, down, left and right. And if there's a resultant force, there's acceleration. Acceleration is a vector, so it needs a direction, which I'm going to carry forward from the first part of my answer. Lastly then, multiple forces in all directions here. Firstly, considering the vertical, we've got an extra 5 newtons acting in the upwards direction. In addition to that, Forces acting in the same direction add together, so we've got 13 to the right but 5 to the left. The difference between those then will mean that we've got 8 newtons left over in the right direction. How do we describe the motion there? Well, we don't need to try and get clever. We know that the motion is acceleration, and we can just include both directions. It is accelerating up and right. In the next question, we're asked to design an investigation here. The keyword is speed. For this, we're looking for the speed of a sound wave. We've already learned speed can be calculated by distance divided by time. So what we're going to suggest is that they record a distance. We want to be specific. The experiment talks about a teacher firing a blank firing gun. The students will see that, and then later they'll hear the sound wave reach them. So the distance is going to be between the teacher and the student, and we also want to suggest a sensible bit of equipment for measuring that distance. If in doubt, something less than the length of your arm, suggest a ruler. Anything longer, let's go for a tape measure. Next, we're going to need to record the time. And again, whenever we're talking about a time, we want to recommend a piece of equipment. Now, this could be a very short time, but unless we're specifically told that the time is going to be less than a second, we are going to recommend using a stopwatch, which is our go-to piece of equipment. With time, you want to say when both the start and the end of timing are. So we're going to start when seeing the flash of the gun going off and stop when they hear the bang, essentially. Oops. Looking for the time it takes a sound wave to reach them. Mentioned earlier about short times. Well, if we've got an object moving incredibly quickly, it can be difficult to measure the time it takes to cover something. That's the situation when a light gate would come in. For toy cars rolling down a ramp, what we'd probably do is put a bit of card on top of it, just like we're seeing here, that would then pass through a light gate. We'd use a ruler to measure the card and the light gate to measure how long it took for the card to pass through. Speed can be worked out from that. Snails racing along a desk, well, they're going to be much less quick, so we can afford a stopwatch. Student walking from one end of the school to the other, you're not going to want to use a tape measure because you're not going to find one long enough, which means you'd have to end up re-rolling the tape measure out. Instead, a trundle wheel is useful for measuring big distances that would take you a minute or more to walk. When investigating trolleys on a ramp where we care about forces involved, we need to make sure that only the forces we're in control of are affecting them. That means getting rid of, or rather compensating for, friction, which is why the ramp is tilted just enough so that it rolls at a constant speed. It's not speeding up because of the ramp, but it's not slowing down by friction either. The moving system in this question refers to all parts connected that move. So not just the trolley, but the string and the hanger with masses pulling on it. The only way to keep that constant is to not add or take away anything from it, which means we just want to move masses between them. If you're doing this investigation, you might load up at the start a load of masses on the hanger and then move them to the trolley one at a time, or vice versa. A velocity time graph is laid out in front of us, and we know that because we've got meters per second at the side, don't really care what the words used are, and seconds along the bottom. As for the car's motion, that means using words like accelerating or not. In this case, 0 to 10 seconds. We're going up. We've got a change in what's measured along the y value, so a change in velocity or speed, and that was our definition of acceleration. Then we're asked when was it stationary, or rather how long for. Stationary is a velocity, or meters per second, of 0. That only occurs from here, halfway between 25 and 30, so at 27.5, to here, the end of our journey at 35 seconds, for a total amount of time equal to 7.5. Acceleration was defined as change in velocity divided by time. Change, therefore, in our side values divided by the change in our bottom values, or rise over run, exactly the same as gradient. So for any straight section of a velocity time graph, the gradient is equal to the acceleration. We could go from 0, 0 to 10, 9, but just for fun, I'm going to choose 2 random points. Let's pick, go up from, where's looking fun? Let's go up from 2.5 seconds, where we hit here, which is roughly equal to 2.5 meters per second. So at 2.5 seconds, 2.5 meters per second, and let's go from, where else crosses somewhere neat? Here's good. So let's go from there, which is halfway between 5 and 10, 7.5 seconds, and that pairs with a speed halfway between 6 and 8, so 7 seconds, meaning my change, always our final minus initial on my velocity, divided by my change, always final minus initial on time, gives me this value to get into my calculator, which will spit out an acceleration of 0.9 meters per second. You'll have got slightly different values. If you chose, for example, 0, 0 and 10, 9, you've got a value of 0.95. Anything in the region of 0.85 to probably 0.98, they'd give you the marks. Lastly, total distance is requested. The neat trick for this is that the area under a velocity time graph is equal to distance. We want to break that up into 2 easy to work out areas. So it asks for the first 25 seconds, basically up to here. Well, I can see there's one big rectangle and one triangle there. So the triangle has got a height of 9, and it went from 0 to 10. And the big rectangle has got a height from 0 up to 9 as well, obviously. But, and this is where you don't want to make a mistake, it went from 10 to 25. So it had a base of 15. Now that triangle, that's going to have an area of half the base times the height, whereas our rectangle is simply base times height. This question, again, we can apply our heist approach from rest, 0 meters per second. Accelerates at constant 1.5 meters per second squared. That unit shows that's our acceleration. Reaches, so a final speed of 6, but we're asked how far it goes. That's a key trigger to tell us we're not using our previous acceleration equations because there's no time mentioned. Instead, we're using this equation here. Final velocity squared minus initial velocity squared is equal to 2 times acceleration times displacement, which is just distance in a straight line. That's what we're after. We'll need all the other bits to be able to plug in, or this isn't the correct equation. So can we find our final velocity? Yeah, that was 6 squared. Initial velocity was our hidden 0 meters per second. 2 is just a 2, and acceleration we're told was 1.5. Let's do a bit of internal maths and simplify this down. 6 squared is 36 minus 0 squared is minus 0, so it's 36 equals 2 times 1.5 is 3. Every equation should come down to just 2 numbers and the thing you're after. Using our rearranging skills, either the flowchart method or my favourite, doing the same to both sides, I see I've got to divide to get rid of a times by 3 to leave question mark on its own, meaning this side becomes 36. Divide by that 3 to give me what I'm after, a final answer then of 12 meters. Energy transfers occur whenever there's any kind of change, so identifying the change that's happening is useful. When brakes are applied, they are getting the movement energy of the car to effectively decrease. So we're going to be transferring out of kinetic. The way they function is that friction, just like rubbing your hands together, causes that movement, that kinetic energy to become thermal. If there's any transfer where you can't figure out where energy has gone and it looks like it's disappeared, instead pick thermal, which is the most likely place that it has transferred to. Headlights, well, out of these options we're given, they're making light where there wasn't any, and they do that when they are supplied with electrical. Both of those are pathways rather than stores, but that certainly is a process that happens. Stereo speakers, the outcome is that we've got sound waves, and once again they only work when electrical energy is put into them. However much energy you put into a device is going to be the same that comes out, even if that energy escapes into the surroundings, is the law of conservation of energy. Almost all equation questions, you'll get every number you need with one exception. The value of G, or gravity, on Earth you must have memorized, and it is equal to 10 newtons per kilogram, sometimes given to you as an acceleration, which is the same, 10 meters per second squared. That's going to come in handy in this question here. We're asked about energy changes gained by something that is lifted upwards by a known height. That form of energy is gravitational potential energy, and the relationship between mass, height, and gravitational potential energy is the change in energy is equal to mass times that value for gravity we had memorized, multiplied by the change in height. Plugging all of those values in, what we end up with is something that looks like this. That law of conservation of energy comes in useful here. Useful energy is often the top energy on a diagram. If 50 joules went in, 20 joules became thermal that we didn't want, that would leave behind 30 joules to be useful. What that would be would depend on the device. In this case, it's a fan. It wants to spin blades and push air. Both of those are examples of movement, so kinetic energy was desirable. Efficiency is a ratio of the useful energy compared with the input energy. Using our answer from before, because this is all related to this same fan, 30 joules was our useful energy out of the 50 that we put in. That is a ratio of 0.6, but we want our answer as a percentage. So what we're going to do is multiply that by 100 to give an answer of 60%. The transfer we're seeing here is also very typical, where the thermal energy that's produced is the waste energy. In increasing efficiency, then, we're often looking to reduce how much energy is turned into the thermal store. Oiling a bike chain will mean less friction, which changes less kinetic to thermal. Double glazing a window is keeping the thermal that we want on one side of the glass, because gases do not easily allow thermal energy to pass to their neighbours by collisions of particles, and closing the curtains would block or reflect the infrared radiation, another pathway through which thermal energy can travel. Lots of information and a tricky calculation here, so we really want to follow our heist approach very carefully. We're told a cyclist and their bike combined gains 4.75 kilojoules of potential energy at the top of a 5 metre tall hill. The total kinetic of them and the bike is measured as 4 kilojoules at the bottom. If the mass is 95 kilograms. What was the velocity of the cyclist at the bottom of the hill? Giving an answer to two significant figures. What we're seeing here is a lot of extraneous information given, stuff that we don't need. For example, we're only looking at the bottom of the hill. This top of the hill and the change in their height isn't relevant to us because we want to use the equation kinetic energy is equal to half times mass, having been given both of those values, multiplied by velocity squared, where velocity is what we're after. There is an extra little booby trap involved here, though, in that the energy we've been given is in kilojoules. So a conversion is necessary to begin with. Down one step from kilo to nothing is multiplying by 1,000. So 4,000 joules was our kinetic energy at the bottom. Half is simply 0.5. We were given mass of 95. And then importantly, velocity is what we're after, but that squared is separate from it. Keep careful track of that squared. We can do the 0.5 times 95 and end up with an answer of 47.5. So to rearrange this, we can divide by 47.5 to mean this side has all the numbers and we're just left with what we're after squared. And to get rid of that squared, we're going to apply a square root to both sides. So this is what we could key into our calculator to give us just velocity on its own. What you'll find is that you've got a number that goes on and on and on, and you don't want to lose track of the fact that you're asked to give it to two significant figures. So you count the first two numbers, and then the third digit you look to see if it's greater than 5. That'll tell you that you need to round up in this instance. You should get a final answer of 9.2. That kinetic energy, though, 4,000 joules, was less than the 4.75 kilojoules, so 4,750 joules. So we've got 750 joules that seems to have disappeared. Again, if it ever looks like energy's disappeared, rather than that, what will have happened is that we'll have dissipated. That means transferred to the surroundings. And almost all of the time, that will be in the form of thermal or heat energy, either via conduction, convection, or radiation. And the cause of that, whenever we've got a moving object, will be because of the friction, either between the parts of the moving vehicle itself, between the moving vehicle and the ground, or even just the moving vehicle and the air. Waves are a method by which energy is transferred. Importantly, they do not transfer matter. If you're out at sea, tides and currents can move you, but the waves will only have you bobbing up and down in place. Waves, though, can be varied by us on purpose to transfer information, just as I am doing now with sound waves. So energy and information, but not matter. Sound is a longitudinal wave. That is the opposite of a transverse wave. The two categories any wave fits in, and that's to do with how the oscillations within them occur. So that word wants to be in our answer. And in longitudinal waves, the oscillations are along the wave in the same direction as travel or parallel to the direction the energy transferred. So I'm going to say oscillations are in the same direction as the wave. Waveform diagrams like this one give us information about a wave. Importantly, they're not a photo of the wave. This one is for a sound wave. It looks like a transverse wave because it's wiggling up and down, but those up and downs just tell us how energetic the oscillations were. In fact, we're even showing this because it says that is measuring volume in decibels. We're asked for amplitude of the wave. Amplitude is always how much they oscillate compared to this symmetrical line in the middle, the rest position. So that distance would be 1 amplitude, and that is equal to 6 decibels. Wavelength, that's how far a wave travels for one full repetition. Now, there's no scale on here for me to measure an individual repetition. Instead, what I'm going to do is notice our wave starts with a peak here. So here's another peak that would make 1, 2, 3, 4, and we end with exactly 5 full waves having happened. That, we're told, took 40 centimetres. So if I take that 40 centimetres and divide it into 5, I'll get the length of an individual wave, being 8. Significantly though, that was in centimetres, and they've been very cheeky and cruel here, and they've said just at the end of the answer line, which we're always reading all the way to the end of, we want our answer in metres. So 8 centimetres, there's 100 of them in every metre, so we're going to divide by 100 for a final answer, 0.08. Next, we want frequency. Still talking about the same wave, and we're given a time. The relationship we're using is frequency is waves per second. The number of waves, we already counted, that was 5. 5 waves per 2.5 seconds means 1 wave would be occurring every 5 seconds. We'll see every 1 second we'll see 5 waves. Hertz is our unit that literally means per second, so 5 hertz is our final answer. Very similarly to before, except in this case we've got a literal physical wave made by ripples in a tank. We're told that they take a photo with a ruler next to it, and we're provided with an image, then asked for the wavelength. Now we could try and read the distance of one individual wave against this scale, but that's going to have a high margin of error. So we're better off using the technique we did on the previous question, figuring out if we're starting there, then this would be 1, 2, 3, 4, 5. I'm going to do 6 full waves because that 6th one lines up neatly with 9 on our centimetre scale. So what we had was 9 centimetres being taken up by 6 waves for a wavelength of 1.5 centimetres per wave. But oh, they've done it again. Hidden within the answer line, we've got metres that our final answer needs to be in. So we're going to take our 1.5 centimetres, divide it by 100 to get an answer of 0.015 metres. That's not true though. If you say that's the wavelength of the wave, the reason being we didn't take a photo of the wave there, we took a photo of what was projected on the screen below it. The light source here had to pass through there to produce an image there, and vice versa. So this distance here is not identical to this distance here. What has happened is that wave, to become projected onto that screen, has been magnified. No tricks in the final question. We're told the number of waves, we're told how long they take. We just need to know that frequency is number of waves divided by time in seconds. So 5, that's telling us every 1 second we had 5 waves